All right, welcome to our third experiment of the semester for Chem 1211 lab here at North Georgia. This is experiment number 5 on the CSE Pub site, the empirical formula lab. So this week's lab, we are going to be trying to determine an empirical formula for magnesium oxide. So as a quick starting point here, we do want to talk about what exactly is an empirical formula, or what does it mean? So most people are probably familiar with molecular formulas from lecture already. Those are just your exact chemical formulas for a compound or a molecule. They tell you the exact number of each atom, the exact number of atoms of each element that are present in the compound that you're looking at. Empirical formulas are the lowest ratio of the elements that are present in the compound. So there will be times where these two things might be the same. So for instance, all ionic compounds, like what we would normally consider molecular formula and empirical formulas, are typically going to be identical. So like we have something that's like CaCl2, that is the empirical formula. It's the lowest ratio that we're always going to get for our ionic compounds. Molecular compounds or covalent compounds like C6H6, if that was our molecular formula, that's not the lowest ratio. The lowest ratio should just be 1 to 1 in that case. So CH would actually be the empirical formula for the molecular formula C6H6. So they are very closely related, but empirical formulas are what we have an easier time actually calculating experimentally if we're examining kind of unknown compounds and trying to find out more about them. Now, finding empirical formulas in terms of kind of the calculational side a little bit, what we really need to know is a mole-to-mole ratio, and that's the most important part here, is that all of those empirical and molecular formulas are all for like the actual either number of atoms, or since atoms are kind of too large of a quantity for us to really measure in terms of how many of them are typically involved in things that we're looking at. We really want mole-to-mole ratios for experimental work. So in order for us to do this then, our main way of being able to go through and find an empirical formula for an unknown compound, if we have an experimental setup or procedure that allows us to find the mass of each of the elements present in a compound, then we should be able to figure out the empirical formula of that compound. By simply taking our masses for each element, converting them into moles, and then getting the actual lowest ratio as far as the number of moles of everything that's left at that point in time. So quick demonstration of that. If we have this, here we have an unknown compound that has 0.230 grams of sodium, 0.355 grams of chlorine. We want to know what's the empirical formula of this compound going to be. Well, all we really want is a mole ratio, so we don't really want the masses, but we can use the masses to get it. Right, so for sodium, we can take its mass divided by its molar mass. It'll tell us how many moles of sodium we have. We can repeat that same process for chlorine. And we see in this case we have about the same number of moles of sodium as we do chlorine. It's not always going to be this perfect of a match in reality, but we can tell by looking at this is a 1-to-1 ratio. So the empirical formula is then NaCl. Like that ratio is actually basically what's going to give us the subscripts for our different elements in our compound for that empirical formula that we're trying to find. Now, in some instances, you're going to get ratios that you can't just look at the number of moles of everything and tell what the exact ratio is, particularly if you start doing this for compounds with more than just 2 elements. And so in those cases, what you can do to try and help better identify what your ratio is going to be is take the moles of each of the elements that you found and just divide them all by whichever one you have the fewest moles of. And now at that point, you should hopefully either have all whole numbers, or you should have all whole numbers that are, you should have all numbers that if you multiplied by a single whole number, will all come out to now whole numbers we can put in a formula. Because remember, we don't want fractions for an empirical formula. Like we don't want like NaCl 0.7 or something. So we need whole numbers for that ratio. And so if you get something where it's like 1 mole of an element compared to 2 moles of another, compared to like 1.5 of the third element, well, that 1.5 is not a whole number. So rather than rounding it, what we'll do is multiply all of those values by 2 in that case. And now the 1 will become 2 for our empirical formula, that 2 will become 4, and the 1.5 will become 3, and now we have all the subscripts effectively that we'll have in our empirical formula when we go to write it for that compound. So that's just kind of a quick introduction to the calculational side of it. What I'd rather spend more time talking about is the actual reaction we're doing this week. So the reaction we're going to be taking a look at is reacting magnesium with oxygen to make magnesium oxide. You can probably guess what the correct empirical formula for magnesium oxide should be just based on charges, but that is the reaction that we're going to be doing to try and find and really confirm the empirical formula for magnesium oxide. Now, the downside for this reaction is that oxygen is not the only thing available in air that magnesium could react with. So even though burning and the actual burning process we always associate as a reaction with oxygen, the magnesium does have the potential to react with nitrogen also to make magnesium nitride. which is a problem because from our experimental setup and kind of design, we want to start with basically just a single strip of magnesium and only magnesium, and end with a strip of magnesium oxide and only magnesium oxide. And that will let us basically then take the difference. We can find the mass of oxygen that's present. We have our initial mass of magnesium, and now we can find an empirical formula with that information. But in order for this to work, we need to make sure that we don't have any of this magnesium nitride in our final product. So how we're going to get around that is we can do kind of a follow-up reaction after we've burned all of our magnesium strip in our crucible. And how we do that is we're going to take a little bit of water, and we're going to add water, just a small amount of water, to our overall product after we've burned it the first time. But before you do this, do make sure that your magnesium product actually cools down. Since it's been heating really hot, you've heated up hot enough to burn the magnesium strip itself. So we want to let it cool down closer to room temperature so we can add the water and actually have this reaction take place. Otherwise, what's going to happen is if you add the water and your product's still hot, the water's just going to hit it, immediately evaporate, and this reaction is not going to happen the way it's supposed to. So we're still going to have magnesium nitride, and some of our data at the end might suffer as a result of that. So let the product cool down. We're going to add water, and then after we added the water, we are actually going to heat it back up to help drive this reaction along. And what's going to happen when we add the water and start heating it up again, the magnesium nitride is going to react with the water to make magnesium hydroxide, and also a little bit of ammonia gas. If you've never been around or kind of seen or smelled, not really seen, but if you've never ever smelled ammonia gas, it's not all that pleasant. It will burn your nostrils. The same thing with if you inhaled it at all. It would also burn your eyes if your eyes get exposed to it. But the good news is we're making so little of that ammonia gas in this process, it's usually not really a concern. Just make sure not to stick your head directly over the crucible as you're doing this step, and there shouldn't really be any problems with this as far as being able to do this reaction on the benchtop. We shouldn't have to do this in a hood or anything like that because there just isn't enough ammonia being produced to really cause a problem. Now, you'll notice at the end of this top reaction up here, we didn't actually make magnesium oxide, we made magnesium hydroxide instead. Thankfully though, if we just continue to heat things after we've added that water for a little bit longer, we can actually convert the magnesium hydroxide into our magnesium oxide product that we're interested in for a final product. And so this gives us now a way that we can burn our magnesium in air and still have kind of a safeguard to make sure that at the end it's hopefully only magnesium oxide that we're going to have as a product at that point in time. And like I mentioned before, once we've reached the end, if we have our final product mass of the magnesium oxide along with the initial mass of the magnesium strip we started with, the difference of those two allow us to find the mass of oxygen. And now if we have the masses for magnesium and for oxygen, we have a way to go through and find our empirical formula. So that's kind of the general process of how the lab works in terms of trying to find out our empirical formula that we're looking for. Now, there are quite a few things I want to kind of make people aware of in terms of the experimental side of this reaction. So first off, as a kind of a quick starting point, the magnesium, when you first pick it up, try to minimize your handling of it with your bare hands. Your hands do have oils on them that if they get on the strip, they can kind of throw off some of your mass measurements because those oils might not burn in air the same way that magnesium does, and so you might get some kind of weird results because of that. The other thing to look out for when you pick up your magnesium strip is if it's got any kind of blackish coating to it, or if it looks kind of dull and it's not shiny. If that's the case, you have kind of a duller strip of magnesium, go ahead and rub its edges, or basically its surface with steel wool. And by doing this, it should hopefully remove that magnesium oxide coating that's kind of formed on your magnesium strip. This should hopefully make it so that we don't have any magnesium oxide already. So when we burn magnesium, it's just magnesium starting out, and all of our calculations should work well. We should hopefully get a pretty accurate empirical formula. If you don't do that, and you have a lot of kind of, like I said, that kind of blackish or dull color or dull appearance to your magnesium strip, that means a lot of your magnesium is already magnesium oxide. And so your initial magnesium mass isn't going to be very accurate in terms of what's actually magnesium or just magnesium there at the start. And so keep that in mind also as you're kind of getting started with things. And then before you actually start burning your magnesium, it's important to make sure you take your magnesium strip and coil it before you go and put it in your crucible. We don't want you to wad it up in a tight little ball because in order for all the magnesium to actually burn for this reaction, your magnesium needs to have as much surface area as possible to interact with the oxygen that's going to be there. So if you wad it up in a little ball, you have a bunch of magnesium that's not really exposed to the oxygen itself, and now it's not all going to burn, and you're going to get some kind of inconsistent final results for your empirical formula as a result. So do make sure you coil that magnesium wire also. And then when you go to actually start burning the magnesium, you want to make sure the crucible is at least open a little bit because you need oxygen to be able to get into the crucible for your reaction to happen. As you do this, though, you don't want your crucible wide open with like no lid, because if there's too much oxygen, the reaction happens too fast, and some of your magnesium oxide product might actually get released as a smoke almost instead. So if at any point you happen to see a white smoke coming out of your crucible, or if you just see a really bright white light coming out of your crucible, make sure to cover your crucible all the way at that point in time and go ahead and remove it from heat. At that point, because at that point you basically heated it too much, there's too much oxygen there, the reaction's going a little bit too fast, and so you're losing some of your product as white smoke, and that light is honestly so bright it can hurt your eyes or damage the eyes of others around you. So just something to kind of be aware of and careful of. If you do see that really bright light, go ahead and just cover your crucible up and take it off the heat, and it should be fine. Now, in terms of telling when your magnesium is done burning, this is probably the most asked question usually during this experiment. What you're looking for is that your metal should now be just a dull powder. It shouldn't really be a shiny strip anymore. The biggest thing is just making sure there's no like metal shine anywhere that's left. It's also probably like, going to be fairly crumbly, like to the touch. If you want to touch it very briefly with like the tip of a pen or a pencil or something, just be careful if you do that because it might stick to the tip and then you might lose some of your mass that way, so it might throw things off too. So usually if you can just visually look at it and tell, yes, it looks like kind of more like it's very powdery now, it's got a very dull color to it and it's not shiny, that's kind of your main indication. You can also, if you're still heating it, if you've opened the crucible fairly significantly and there's no white smoke or anything coming off as it's heating and all you see is maybe like a dull red glow, then at that point it should have been pretty much all the way burned and hopefully converted to magnesium oxide, or magnesium nitride also is a possibility. Now, to do this whole experiment, we are going to be using Bunsen burners, and I'm going to give kind of a visual demonstration of this here in just a minute as well. But some just kind of quick written things that you can reference this back while you're doing the experiment. When you go to use your Bunsen burner, make sure it's hooked up to the right valve. You don't want to hook it up to water or air. Water in particular, you get a very unpleasant surprise when you go to turn on the valve. So make sure it's hooked up to the gas, which is going to be the valve that has the blue cap on it. And then when you go to turn on your gas valve, you should hear a little bit of a hiss of the gas itself coming out of the Bunsen burner. Once you hear that hiss, you know the gas is flowing. Don't wait very long. Use your striker. Take your striker, put it right near the tip of the Bunsen burner, and go ahead and strike it to ignite. And that should light your Bunsen burner. You should have now a flame that you can control. And then when you're done with the Bunsen burner and you're not burning anything anymore, just go ahead and shut off the gas at the main valve. Don't let it sit there burn unattended, and also don't shut it off just at the bottom of the actual Bunsen burner. That is absolutely never what you should do to shut the Bunsen burner off, because that would just cause some other issues potentially as far as gas buildup. And you want to make sure that there's not gas just flowing that's not burning either, because if there's a big buildup of gas and there's a bunch of people in the room with strikers lighting their own Bunsen burners, now we have kind of this potential for some kind of very, very big flashes of flame that are not necessary. So just we want to make sure we take very good care and caution as we're using our Bunsen burners. And like I said, just kind of follow the simple steps. And I'll have, like I said, a complete visual demonstration here in just a moment of all these things. The last things I do want to highlight there before I show a visual demonstration of that, though, talking about just general disposal, some cleanup, and some things about crucibles. Your final product, when you're actually done with this experiment, can actually just get thrown in the trash. Just make sure it's cooled down some. You don't want to throw a really hot product in the trash because there's often things like paper towels or things that are potentially flammable that if your product's hot enough, it might set them on fire. So just make sure your product's cooled down enough. You can just go in the garbage, that's fine. And to clean out your crucibles, go ahead and wipe them out with a paper towel, but do not use water in this instance. Pure magnesium, if there's any left that hasn't reacted, which there shouldn't be a lot of, but it is possible, pure magnesium actually reacts pretty violently with water. And so you want to avoid that, because if you don't want to actually cause that reaction to happen at that point in the crucible when you're cleaning it. So just wipe it with a paper towel. That'll be sufficient to wipe things clean for the next groups that are going to use them. Now, one thing that will happen in this experiment, crucibles will crack and break. Obviously, that can happen through just being dropped or kind of like air on the student's part of handling it. But also it can just happen in the normal course of heating and cooling something down over and over that's made out of ceramics. Like, it's gonna break over time. That's just something that happens to these crucibles. So do pay attention to your crucibles as you're using them. If you get to the end of like your first trial and you notice there's some really big cracks that have kind of formed in the bottom of your crucible, just notify your instructor, switch that crucible out for a newer one. because that cracked one is probably not going to survive your next attempt. Because during its heating and cooling cycle, it might break in the middle of your experiment, and now you have to restart that whole trial. And so just kind of pay attention to those. It's not a big deal if you do drop something and it breaks, although do try to take caution. If anything does break, or if you're worried that something is going to break because it's already kind of cracked before a trial starts, please just notify your instructor, show it to them to take a look at it quick. We can get it switched out. If you do need to throw something away for the crucible that's broken, make sure it goes into the glass waste, not a normal trash can. Because those ceramics, especially if they're broken, are going to likely have sharp edges, much like glass would, and so we want to make sure it's not a normal trash can because of that. And probably the last thing I would mention here in terms of your crucibles, if you do break one, if the instructor comes over to, or if TA comes over to try and help, please tell them whether the crucible is hot or cold, because just looking at it, it's not usually easy to tell whether that crucible is hot or cold. And we don't want like an instructor, the TA, just reaching down to grab it and burning themselves because it's actually hot and you didn't say anything about it. Hopefully they would use caution before they go to do that, but that is just kind of hopefully common convenience towards them. Just tell them whether your crucible is hot or not if something does happen and yours is broken.
Alright, welcome to a quick demonstration here of how to use the Bunsen burner and what the experimental setup is going to look like for our empirical formula lab. So when using your Bunsen burner, first thing that you really want to make sure you get it connected to the right valve options that you have here. So we have 3 different possible valves you can really connect to. Make sure you do connect it to the one that has the blue cap. That's the one that's going to have gas. That's the only thing that's actually going to get a flame out of your Bunsen burner. Orange is air. Green is water, which will lead to a very wet surprise if you happen to get up there. So make sure it goes on to the blue cap. And once you've connected your hose to the actual spigot on your gas valve, to turn it on, you're just going to turn the knob so it's in line with the spigot itself. You should hear a slight hissing and probably even smell a little bit of the gas coming off. If you put your striker down right over the top of it, you should actually get to light right away. And then once you have your flame on, you can actually adjust it a few different ways. The top twists both directions, which adjusts how much air is flowing through, and so you can see it adjust the cone shape a little bit as you're kind of doing that. Or you can adjust the bottom, which is how much gas it has access to, and so you can adjust the flame size that way as well. And what we're looking here for is what we want out of our flame is we want kind of a nice tight inner blue cone, and like what I've created right here. So the inner blue cone, what you're going to want to do for your setup here is you're going to want basically the tip of that blue cone right up against kind of the bottom of your ceramic crucible. Now, when you go to put the Bunsen burner under it, don't just jam it under it and blast it full bore with heat. Kind of gently waft the flame under it for a little bit first, so you can kind of slowly let that actual ceramic crucible warm up. Since it is ceramic, it's like glass, it will basically expand as it warms up, and so if it's a really big temperature change, it can kind of shock the ceramic into cracking because it's trying to change its size and expand too fast. So just be gentle with it. Once you've done that a little bit, you can go ahead and set your flame underneath, and you can either adjust the height of your ring stand, or you can adjust the height of the flame to try and match where your crucible is. Either way, what you want is kind of the tip of, like I said, that blue flame to be more or less touching the very bottom of the crucible. And what you should see is after a little bit, you should see the bottom of your crucible start to glow red. Now, when you go and set this up, before you put the Bunsen burner on here, kind of like what I have, make sure you actually have your lid properly on your crucible. So for setting up your lid, one thing you do want to make sure you kind of keep in mind is that in order for your magnesium to burn, you need some of your crucible open, but you don't want it full bore open like what I had when I started to set it up. Because what happens is if it's fully closed, there's no oxygen getting in to cause the reaction to happen. But if it's just full bore open, then there's the problem that there's too much oxygen getting in, and then as a result of that, you're going to see basically it burn too fast. You're going to see a really bright white light and probably some white smoke being given off as well. If you do see that start to happen, you can just take your tongs, go ahead and kind of close back the crucible cover, and then what you can do is just go ahead and remove the flame from underneath it. If you do that, let it sit for a couple minutes. The fire should kind of slow down. You shouldn't really have any smoke or any that white light being given off anymore. So give it a couple minutes. You can open it, check it. Should be good to go. When you're done with the Bunsen burners, or if you are just not standing right next to it, not actively using it, please shut them off. And when you do that, make sure to do it at the gas valve itself. So just turn the gas valve back perpendicular. That'll shut off the gas flow. Will shut off the Bunsen burner. Don't leave them unattended with the open flame. It's just kind of a safety hazard. I think it's pretty self-explanatory. And don't shut them off at the bottom of these things either. Otherwise, they can still be leaking out gas in the surroundings, and if everyone else is using open flames around you, that's a potential problem. And so just always make sure shutting the Bunsen burners off at their valve up here. Other than that, hopefully that's kind of a nice quick demonstration, so you'll be a little more familiar, kind of a better idea what to expect for using your Bunsen burners this week. If you have any questions, make sure to ask your TAs, your instructors. We're here to help.